happy to have José Luis Pérez from CIMAT speaking at our seminar. In ASU, we are particularly happy because it's the first time we try to do a mix online in presence with 3 participants, but we will improve the number very soon. And yeah, thanks a lot. Now we are 4. Perfect. So José Luis is going to talk about fluctuation theory for spectrally negative Lévy processes, killed by an additive functional and applications to penalization problems. Thanks a lot for that.
Thank you very much. So first of all, I would like to thank you for the opportunity to speak at the seminar. So yeah, I'm going to speak about these fluctuation identities for spectral negative Lévy process and additive functional. So this is joint work with Kei Noba, Kohki Ibba, and Kouji Yano. So the main idea behind the talk is that we will have a spectrally negative Lévy process, and then we'll have an additive functional associated to this spectrally negative Lévy problem. And then we consider an exponential random variable, parameter 1, and we evaluate this exponential random variable in the inverse of the additive function. So this gives a random time or a clock, and whenever the clock rings, we kill the spectrally negative Lévy process. And the idea is to obtain certain kind of identities, like solutions to the two-sided exit problem, how the Lévy process, when killed by the additive functional, exits a strip, expressions for the resolvent density, and to generalize results obtained by Palmowski and Li for the case in which the additive functional is absolutely continuous with respect to the Lévy measure, which is what is known as the omega kill spectrally negative Lévy process, which has many applications in finance and insurance. And then the main idea is to use this type of identities to study another problem, which is what is known as the penalization problem, which was introduced seminally by Ronet, Valois, and Jor. And it's basically taking Brownian motion and penalizing the paths of Brownian motion according to a function of local time. So they showed that when we penalize in a finite time window and we take the window go to infinity, this converges to a martingale change of measure. And under this martingale change of measure, we can obtain a concatenation between a Brownian bridge and a Bessel process. And this is interesting because for particular choices of the penalization, we can obtain new versions of conditioning a Lévy process to avoid 0, which is important, for example, to study the excursion measure away from a point for Brownian motion or for a Lévy process. Okay, so let me introduce the main objects in this talk. So the first one will be a spectrally negative Lévy process, which is a really simple process, which has a stationary and independent increments. And spectrally negative means that we will consider that we only have negative jumps. So in this case, the Lévy process is characterized by its Laplace transform in terms of what is known as the Laplace exponent. And the Laplace exponent by the Lévy-Quintin formula has the following expression. So we have the linear term, which I denote by gamma, the Gaussian term, and the Lévy measure, which is simply characterizing the jumps of the process. And we have the general assumption that the minimum between 1 and zeta squared is finite with respect to the Lévy measure. And in this case, it is concentrated on the negative half line. And of particular interest for us will be the case in which the Lévy process will be of bounded variation. This happens only if the sigma term is equal to 0, the Gaussian term, and we have a stronger assumption of the Lévy measure, which is simply that the minimum between 1 and x is finite with respect to this measure. And in this case, the Laplace exponent takes a simpler form, which is given by this expression right here. And we consider the drift term, which is finally defined by this function right here, which is the linear term and the compensation by the jumps. And this will be quite important for most of our results. And why I say because it's of particular interest, because most of the results for the bounded variation case are more interesting than in the case of unbounded variation Lévy processes. So this is the first object. So this is the object I want to kill, which is this spectrally negative Lévy process. And then I will introduce the second object, which is what is known as an additive functional. So what's an additive functional? So I will working with a particular case of additive functional, which is what we denote a positive connatural additive functional. So in the theory of Markov processes, we have really general additive functionals like row additive functionals. But the main difference, I think, is the structure of the jumps. But because we're working with Lévy process, we have no branching points, so this source of jumps does not appear. So basically working with this kind of additive functionals is mostly the most general case. And in order to define a positive connatural additive functional, we need to define two things. The first one will be a defining set, which is what I call here by omega A, which is a subset of omega in which the additive functional is defined. And then is what is known as deceptional sets, which the complement is exactly the set of starting points for the Lévy process in which these properties of the additive functional is defined. But for spectrally negative Lévy process, one can prove that this set of exceptional points is empty, and therefore everything holds for any initial state. So what's a positive connatural additive function? Simply it's a stochastic process that satisfies the following. So the probability of the defining set is always equal to 1. When we apply the shift operator to the defining set, it lies in the defining set. This is important because it will allow us to have this property, which is called the additive property, which is, I think, the most important property of an additive functional. And then we have that for any omega in the defining set, the additive functional is non-decreasing, non-negative, right continuous, and it starts at 0, right? And about the jump structure, which is one of the most interesting things for this type of additive functional, is that any jump of the additive functional is given in terms of a measurable function, which I denote simply by f of a, such that the jump simply is this function evaluated on the Lévy process. So these kinds of jumps are called non-accessible jumps for additive functionals. And then we can have another source of jumps for a more general additive functional, but these are known as left additive functionals, but there's a bijection between them. So basically, studying this case of connatural additive functional is enough for us at the moment. And finally, an additive functional satisfies what is known as the additive property, meaning that if we look at the additive functional at time s plus t, it's equal to looking at the additive functional at time t plus the additive functional at time s, but shifted by the shift operator at time t.
Yeah, I have a question just to be sure. When the process makes a jump, like this difference between AT and AT minus, it's a functional of xt, not a functional of the jump that xt makes?
No, it's a function of the process, not of the jump.
Okay, thank you.
But yes, but this is quite important also because the other type of jumps, it will be a function of the jump, of the Lévy process and the left limit. So you can also have that, you can consider the jump by itself, right? But for this particular class, it only depends on the Lévy process at time t, for the jump of the additive functional at time t. That's the structure. Yeah. Okay. So, well, and this is the most important property of the additive functional. And let me give some examples just to fix ideas. So the first one is the case in which the additive functional is absolutely continuous with respect to the Lebesgue measure. In this case, we have that there exists a measurable function, which I denote simply by omega, such that the additive functional is simply the integral of omega in the Lévy process, ds, right? So this is exactly the case studied by Li and Palmowski, which is what is known as the omega cubed Lévy process. And we can think of this function omega simply the rate at which the clock defined the additive functional to ring, right? And the second most known example in the literature of an additive functional is what is known as local time. So local time will be simply a stochastic process, which only increases when the Lévy process reaches the level A, so local time at A. And we have two definitions. For the case when the X has paths of unbounded variation, because in this case we have that any point is regular for itself, for a spectrally negative Lévy process, we have that we can formally define local time simply as this limit when epsilon goes to 0. And it's shown, it's a quite classical result, that this limit holds in L2 uniformly in compact sets of time. And also that under some conditions, we can find a version of local time which is continuous in space and in time, right? And the case of Lévy process with bounded variation paths is a little bit different, because in this case, the sets of times in which the Lévy process reaches any level will be discrete. So now we cannot use this definition. So we adopt another definition, which is due to Porton Fitzsimmons, which tell us that for the case that the Lévy process has bounded variation paths, the local time will be simply 1 over the drift term of the Lévy process and the occupation time of the Lévy process at time A. So what's interesting is that this is a right continuous process, which is important because this is the kind of additive functionals that we want to work with. The only problem is regularity in space, because we will need this. Because this is difficult to show that for a Lévy process, this is right continuous of left continuous. So sometimes we use another definition of local time, but we can show that they're equivalent, meaning that they are equal for every t for Lévy almost every level A. But anyway, this is mostly the definition that we're working with for local time when the Lévy process has paths of bounded variation. Okay, so these are the most known examples that have been studied in the literature. And in order to extend the results known in the literature to the general case, I will specify certain properties of this kind of additive functionals. And for this, I will introduce an object associated to the positive connatural additive functional, which is what is known as the Resumo measure. So the Resumo measure, it's simply defined as this limit. And here I forgot to say, but the reference measure that we'll be using for the additive functional will always be the Lévy measure because it's a potential for the Lévy process. So it simplifies most of the proofs a lot, right? So this is the definition of the Resumo measure. So why is the Resumo measure important? Because as we will see a little bit later, the Resumo measure will characterize the additive function, meaning that if we have two positive connatural additive functionals which have the same Resumo measure, then that will be equivalent, meaning that we can obtain a defining set in which the two additive functionals be equal for everything, right? And we will see that we can go a little bit further than this and use the Resumo measure to construct the additive function, right? And so the Resumo measure in a certain way acts like the infinitesimal generator for a Lévy process, right? Okay, but for spectrally negative Lévy process, we can prove a really important property about the Resumo measure of the additive function, which is the following. So for a spectrally negative Lévy process, the Resumo measure associated to a positive connatural additive functional, it's always radon. This is quite important for most of the proofs. And also, we have the converse, that if we take any radon measure nu, we can always find a positive connatural additive functional A, such that its Resumo measure is equal to nu, right? So this is a known result, for instance, for the case of continuous additive function, which is a particular case of this type of additive functionals, and for Brownian motion, for instance. So, but we extend this result for a spectrally negative Lévy process and this more general type of additive functions, right? And one of our key results is the following: how to construct the additive functional using the Resumo measure. And is the following. So imagine that we have our positive connatural additive functional A, and its associated Resumo measure, which I denote simply by mu A. Then the additive functional can be seen simply as a mixture of local time at different levels with respect to the Resumo measure, right? So basically, we have the Resumo measure, and we can reconstruct the additive functional simply by having this mixture of local time at different levels with respect to its associated Resumo measure. And conversely, whenever we have any radon measure mu, then this stochastic process will be a positive connatural additive function. So this is the main characterization of positive continuous additive functionals for Lévy process. For Markov process, this is not always the case. We need certain properties that, well, we can only prove at the moment for spectrally negative Lévy process. And the main idea is to show that a measure which is lambda smooth is equivalent for a spectrally negative Lévy process to being a radon measure. Okay, so why this is interesting? Because the main idea to obtain our fluctuation identities will be to discretize the Resumo measure. So if we can approximate our Resumo measure by a finite atomic measure, and we can obtain the fluctuation identities for this finite atomic measure, then we can extend the general result using this representation to the general case. So this is basically what I'm going to do. First, I will obtain the fluctuation identities for finite mixtures of local time, and then I will extend the result to the general case simply by approximation. Okay, so before I do this, let me speak to you a little bit about the fluctuation identities that I will be looking for. And I will do this for what is known, which is for a spectrally negative Lévy process. So, okay, so in order to specify these fluctuation identities, I need to introduce what is known as the scale function of the Lévy process. So the scale function, it's a similar object to that of diffusions, right? And it's simply a mapping that goes from R to R plus, such that it takes the value 0 in the negative half line, and in the positive half line, it's a strictly increasing non-negative continuous function, which is characterized by its Laplace transform. So the theta Laplace transform of the Q scale function, it's simply given by 1 over the Laplace exponent of the Lévy process at theta minus Q, for any theta greater than the inverse of the Laplace exponent of the Lévy process. So scale functions, because they are used to obtain these fluctuation identities, have many applications. For instance, in stochastic control, in optimal stopping problems, and also in applications to finance, insurance, and many other areas. So this is why they have been widely studied. So for instance, we know certain regularity of the scale function. For instance, if the Lévy process is of unbounded variation, then we know that it's continuously differentiable. And if not, it's differentiable almost everywhere. And the behavior is 0, which will be quite important for us, is that it's 0 if the Lévy process has unbounded variation packs, and it's equal to 1 over the drift term when x is of bounded variation. And finally, I introduce another scale function, what we call the second scale function, which is simply 1 plus, this is equal, 1 plus q and the integral of the first scale function. And why they are important? Well, basically because it solves the exit problems for spectrally negative Lévy process. In which sense? So I define this stopping time, which is the first up-crossing time of the Lévy process above the level A, and the down-crossing time, tau 0, which is the first time that the Lévy process goes below the level 0. So here, what I'm saying is I'm obtaining the Laplace transform of the time that it takes the Lévy process to exit the strip given by D and A when it exits the strip from above. And in this case, it's simply given by this ratio of the scale function. So this is basically the same identity that we have for diffusion, right? And because we have jumps, then the second is a little bit different, but more or less. But here we have the time that we leave the strip when we leave the strip from below. And it's given now in terms of these two scale functions. And what's really important for us, this is the main reason that we wanted to obtain these fluctuation identities, is that we can show that the resolvent measure of the Lévy process is absolutely continuous with respect to the Lebesgue measure, and it has a density. And this density is given in terms of the scale functions of the Lévy process, right? So this is type of fluctuation identities that we want to obtain for now our killed spectrally negative Lévy process. So now that I know the fluctuation identities that I want to obtain, let me tell you about some known results. So the first one is the case when the additive functional is absolutely continuous with respect to the Lebesgue measure. So here we have a locally bounded measurable function omega, and Li and Palmowski obtained the following identity. So now they obtain that the two-sided exit problem from above and from below is given as the same way that for the spectrally negative Lévy process, but now with these two functions which I denote by omega, W omega, and zeta omega. And of course, also that the resolvent, when we kill the Lévy process by this additive functional, is given exactly in the same way as for the Lévy case, but with these new functions, W omega. So in the Lévy case, we could characterize the scale functions simply by this Laplace transform, but in this case, they become a little bit more complicated. So now there will be the unique solutions to these integral equations. So they are these Volterra equations, which are driven by the scale function of the Lévy process, here by 1, and that's it. So this is the identity. So it's a little bit more complicated, but we have these algorithms in order to obtain at least numerically the solution to this integral equation. And now there's also a generalization done by Rivero and Contreras, in which now we have that the additive function is a function of the Lévy process and the supremum of the Lévy process. And in this case, it's not that explicit, but one can show that the scale function is simply given by this expression, where n is simply the dispersion measure of the reflected process. The problem with this identity is that in order to obtain the scale function, we need to know the dispersion measure, and this is quite complicated. So most of the time, we obtain information from the dispersion measure by using the scale functions. But anyway, so we have this expression right here. And the second one I want to show is about local time. But for this, let me introduce a series of functions. So I will consider that I have a positive sequence of numbers and an increasing sequence of real numbers that are greater than C. And now I introduce these functions. So this function at the level K, considering Pi to Pk, P1 to Pk and A1 to Ak, it's simply given by this expression, recursive expression, which is the function at the level K minus 1. We have these weights, and then the function at the level K minus 1, at the same for the function C. And we have the initial conditions that at the level 1, it's simply given by the scale function of the original Lévy process, these weights, and the scale function of the Lévy process. So basically, we can think that level 0, these functions are simply given by the scale function of the Lévy process. And just that in the case that the Lévy process has bounded variation packs, then we can think delta going to infinity. So this is thought in the limiting sense simply as P, right? So with these functions, then I can show the fluctuation identities for finite mixtures of local time. So now, if we consider that the additive functional is simply given by a finite mixture of local time, then we have the two-sided exit problem upwards, exactly the same as in the Lévy case, but with these new functions. And downwards is given in terms of these new functions, except in the same way as in the Lévy case, and we also have the resolvent density. So this allows to obtain these fluctuation identities for these two types of additive functionals: local time, or finite mixtures of local time, and the absolutely continuous case. And this will be our second case, because as I said, now we obtain the fluctuation identities for this particular class of additive functional, which is a finite mixture of local time. So now we can think about this limiting procedure. The problem is that when we think these functions in this recursive way, it's difficult to take limits. So I will obtain another characterization of these functions. But for this, I just provide an auxiliary result, which is a more general result about existence and uniqueness to integral equations driven by Radon measures. So what we have is, consider that we have a locally bounded function, h, and two Radon measures, nu and lambda. And I consider this integral equation, which is driven by the function h, and this charge, which is the difference between these two Radon measures. So if we have this condition on the atoms of the charge nu minus lambda, which is that this infimum is greater than 0, then there exists a unique solution to this integral equation. And furthermore, if h is positive and this is a measure, then we have that the solution is always non-negative. Okay, so why this condition? Well, the problem is the atoms. So one really needs to control the atoms of the charge nu minus lambda, especially when we have accumulation of atoms at a certain point. So in the case, for instance, when the charge is diffuse or absolutely continuous, for example, like in the omega case, then proving existence and uniqueness to this integral equation is quite straightforward. But when we have atoms, things become a little more complicated. For instance, when we have atoms, now we have that the solution to this integral equation will no longer be continuous, but it has discontinuities whenever we have an atom of the measure nu minus lambda. So in order to be able to control the atoms, we impose this condition right here, and we can show that there is actually a unique solution to the integral equation. Without this control, proving the uniqueness is not that straightforward, and we're pretty sure that it does not hold. But anyway, so we have this general existence and uniqueness result for this type of integral equations, and now we have the characterization. So these functions at the n level are simply given as the unique solutions to these two integral equations. Now, the ones they are driven by the function, the scale function of the Lévy process, but they are driven by this new measure. And this new measure, it's simply given by actually the measure of that we're using for the finite mixture of local times, but we are just changing the atoms in this way right here. Right. So with these two key results, now we can extend our fluctuation identities to the general case. So I will roughly tell how we can do this, right? So first, I will just introduce some notation. So I denote by M simply the space of random measures on R. And I will take any random measure and decompose it in its atomic and its diffuse part, right? So I will consider the atomic part has this expression right here. These are the atoms and the weights. And the operator T acts in the measure nu in the following way. So it leaves the diffuse part of the measure exactly the same, but it changes the atoms of the atomic part simply by this expression right here. So in the case that we have that the additive functional, it's simply a mixture of local times with respect to this measure right here, which is given by this expression. Then we have that the operator T applied to the measure nu in which we're doing the finite mixture becomes this one. So basically what we have is that the integral equation is exactly the same, but here we have the operator T applied to the Resumo measure. And this is exactly the result that we want to obtain. But first of all, I will need to know how to discretize the measure B, right? Especially the diffuse part of the measure. And for this, well, we take the radon measure, we decompose it in its atomic and its diffuse part. So how to handle the diffuse part? Because we want to discretize it, the most easy way of doing this is using a randomization technique. So basically to condense the mass of the diffuse part of the measure into atoms. And for this, we use a Poissonian discretization. So we consider the independent Poisson measure, which I denote simply by NN, which has this intensity measure, which is n times the diffuse part of the measure. And because the measure is diffuse, then we have that the atoms, that the measure is a counting measure, and also that each of the atoms has a weight 1. And I will define this new random measure, which is the atomic part of the measure, and this Poisson random measure. And with this, now we have everything that we need, because it's quite easy to show by construction that this sequence of random measure converges as n goes to infinity to our original measure, vaguely in L1, because now we have this random measure. So this takes care of the convergence of the left-hand side of the identities. But what about the right-hand side of the identities? Well, for this, we have this approximation result. So now I consider that I have this sequence of stochastic processes, which are simply given as solutions to this integral equation. But now, because the measure nu n is a random measure, then we have like a random Volterra equation or integral equation, because what we're actually doing is obtaining the scale function of a discrete mixture of local times when the levels are random, because we are randomizing the levels using this Poisson random measure. But the thing is that as we take n to infinity, then this sequence of the stochastic process converges in L2 uniformly in compact sets of space to the unique solution to this integral equation. And this is exactly the type of integral equation that we were doing. And we have the same result for the function theta. So now we have this new sequence of the stochastic process, which are the unique solution to this random integral equation. One can show that almost surely the solution exists because it satisfies the assumption of our existence and uniqueness theory, right? And then the sequence also converts in L2 to the unique solution to this integral equation. So with these two results, we have exactly what we need. So now, roughly, let me tell you how we obtain the fluctuation identities. So I consider A, which will be my positive connatural additive function of my Lévy process X, which is associated Resumo measure nu. So what do? We decompose the Resumo measure in its atomic and its diffuse parts. And then I randomize the diffuse part of the measure using an independent Poisson random measure with this intensity. And I consider this sequence of random measures, which now they are counting measures, right? So with this is exactly the type of identities that I want to obtain. But I know that I can express the additive function simply as a mixture of local time with respect to its associated Resumo measure. And then we have that the Resumo measure can be approximated by this sequence of random measures nu n. So I can take this limit out. One has to be careful because we need to handle the discontinuities of local time, because in general it will not be continuous, but one can show that everything holds. And then what I do is I condition with respect to the Poisson random measure. So in this case, we have that now this measure will be an atomic measure, and we know how to handle these identities were simply given by this ratio of the scale function. And we know that they converge in L2. If I take a limit, one can show that this converges to this expression. And we are done. So basically, this is a really simple idea to obtain the general case, but it actually works, right? So with this, now I will show quickly our main results. So for a general positive connatural function A of the Lévy process with this Resumo measure, then we obtain that the fluctuation identities or the solution to the two-sided exit problem when the Lévy process killed by this additive functional, it's simply given exactly the same by this ratio of the scale functions, and the scale functions are now the unique solutions to this integral equation. And just to fix idea, let's see what happens when the additive functional is absolutely continuous. So in this case, because it's absolutely continuous, its Resumo measure is simply given by the function omega and the Lévy measure, because by the occupation formula for local time. So this measure is diffuse, so the operator t disappears, and here we only obtain the function omega ds, and we recover the results of Li and Palmowski for the absolutely continuousness. But of course, here we have a more general result. We have the solution to the two-sided exit problem downwards, exactly the same in terms of these scale functions, which are the unique solution to these integral equations. And finally, what we were really interested in, which is the resolvent. So the resolvent measure of the Lévy process killed by a general positive connatural additive functional will be absolutely continuous with respect to the Lévy measure, and the density is given simply by this. So once again, it's actually the same for as in the Lévy case, but with these new scale functions, which are these solutions to these integral equations, right? And just to finish this part of the talk, I want to talk a little bit about these integral equations, right? That we have obtained in order to characterize the scale functions. Because what we have observed is that when for a more general type of Markov processes that can be obtained from Lévy process, like refraction, certain type of jump diffusions, time change or measure change Lévy process, we can always find that the scale function is actually a solution to a Volterra type of equation, but it's a little bit different. For instance, here, if we have the generator of a process applied to this, we can have some jump diffusions, refraction, for instance. Here, when we have weight here, it's simply mean killing. When we have a function multiplying the integral, we have a time change, and so on and so forth. So basically, we can obtain scale functions for more general type of Markov processes using Volterra equation. So it's a really interesting question behind this, right? So we have a really general Volterra equation. Can we find a Markov process such that the scale function is the solution to this integral equation, right? So there's an interesting problem behind this, characterization of scale function for microprocess using Lévy processes and Volterra type of equations, right? But anyway, so now I will turn to really the problem that we were interested in studying, which is the penalization problem. And the main result that we will be using is simply the expression for the result. Okay, so let me speak a little bit about the penalization. This penalization was introduced, as I said at the beginning, by René Boulward for the case of a Brownian motion. And simply, it consists in penalizing the paths of Brownian motion using local time. So basically, what we have is a Brownian motion, and we consider LT, which is the local time at 0. So we consider an adapted functional of Brownian motion, which I denote simply by f of t, an integral function of f, and I will consider this type of identities. So I simply take the bounded functional of Brownian motion and multiply by a function of the local time. So this function of local time is what is penalizing the paths of Brownian motion, and they are normalized by the penalization. So here I'm penalizing onto the time window given simply by s. And then, for instance, to fix ideas also, imagine that the function f is simply the indicator at 0. So in this case, the only paths that survive are those which haven't touched 0. So basically what we will have here is simply conditioning until time s, the Lévy process to avoid touching 0 until time s. And then we take the limit when the time window goes to infinity. So René Boulward show that this converges to this expectation, where the process mt is given simply by this expression right here in terms of the absolute value of Brownian motion and this integral with respect to local time. And they showed that this is a martingale, so this is actually a martingale change of measure. And under this marginal change of measure, one can show that Brownian motion behaves like a concatenation between a Brownian bridge and then a Bessel process, because eventually we're conditioned to the Lévy process to our T. And this result has been extended by several authors. For example, Debs extend the result for random walks. Nudel, Renat, and Jor for the case of Markov chains and Bessel process. Yano, and Jor for the case of symmetric stable processes. Salminen, Valois, and Profeta for linear diffusions. And then we have a really general result by Profeta, Yano, and Yano, which is a general theory for one-dimensional diffusions. But the difference is they use this random group approach, which is what I'm going to talk about right now. So basically, recently, Yano and Takeda studied the case of penalization, but for a Lévy process. So we'll consider a Lévy process, which is not a compound function process, and such that zero is regular for itself, meaning this property directly. And then we define this heating time of any Borel set by this expression right here. And they were interested in the same type of penalization results. But the only difference is that instead of taking the time window in which we make the penalization to be deterministic, now it's random. And they use what they call random plots. So they analyzed 3 different types of random plots, which is the exponential plot, when tau is simply an exponential random variable parameter q. The heating time plot, which is simply the first time that the Lévy process reaches the level A. And the 2 heating time plot, which is the first time that it reaches the level A or the level B. And because we want the time window to go to infinity, they consider the case in which Q goes to 0, A goes to minus or plus infinity, and A and B goes to infinity, right? So what type of results they obtain? Well, first, they make this assumption on the Fourier exponent of the Lévy process. Under this condition, one can show that the resolvent is absolutely continuous with respect to the level measure, has a density which I denote by RQ, and we define this function HQ, which is this difference. And for this, under this particular condition, one can show that the limit as Q goes to 0 of this function HQ exists, which is what is known as the normalized resolvent. And then we define a new function, H gamma, which is given by the normalized resolvent, and this quantity right here, where M is simply the second moment of the Lévy process. And under these conditions, they obtain the following result. So consider that we have a positive integral function f, and this is the stochastic process, where it's given in terms of this function h gamma, which I defined before, the function of local time, and this integral with respect to local time. And I will use this notation. So AB goes to infinity if A minus B divided by A plus B goes to gamma when A and B go to B. So under these conditions, they obtain the following result. That in the case where the martingale is positive, surely at 0, then we have the following penalization. So the penalization with the exponential clock converges as Q goes to infinity to this martingale change of measure with this martingale when gamma is equal to 0. It converges for the heating time clock when A converges to plus or minus infinity to the martingale and minus or plus 1. And when A and B goes to infinity in this, under this definition, to this martingale M of them. So basically what Yano and Takeda obtained were simply generalization of these penalization limits. So they obtain a new class of penalization limits. And of course, when one takes as F the indicator at 0, then we obtain different conditionings of the Lévy process in order to avoid 0, right? So this is exactly the type of setup that we want to work with. But what we want to obtain is a more general class of penalization limits, right? By generalizing the clocks that we're using in order to make the penalization. And for this, we use additive functions, right? So we will use random clocks that are characterized by the additive functional of the Lévy process. So for this, I will consider a recurrent spectral negative Lévy process, which for simplicity has been 0. And I will consider a positive connatural additive functional of the Lévy process. And because it's an increasing process, we can define the inverse. And I will consider an independent exponential random variable of parameter 1. And I define this random time, which is simply the inverse applied to this exponential random variable. So one can show that the probability that the clock rings at time greater than t simply is equal to this quantity, and we have this exponential term. And it's exactly the killing that we have in the previous identities that we obtained, especially for the result. And just in the case of Takeda and Yano, the essential object to study in order to obtain the penalization results was the resolvent density. So this is why we wanted to obtain explicit identities for the resolvent density when we kill the Lévy process by this additive function. Okay, so now we'll show our main penalization results. So I will consider now a clock, which is simply, I will consider this class of positive connatural additive functionals that will be parameterized by this epsilon between 0 and 1. And I will denote Resumo measure, but if of the positive connatural additive functional simply by nu A epsilon, right? And we have this assumption. We have a lot of assumptions because it's a really general type of plots. But for simplicity, we assume that the Resumo measure acts like Q or P, the Lévy measure when it's above gamma or below 0. Q and P converges to 0. The Resumo measure converges weakly to 0. And then we have these identities which are simply related to the Lévy process, right? In terms of its inverse Laplace exponent. And finally, the stronger assumption is that we have that this charge, which is the Resumo measure minus this absolutely continuous measure, converges to a measure which I denote simply by nu tilde in total variation. So under these conditions, we have our following penalizations. So with this sequence of random clocks defined by this expression right here, the inverse of the additive functionals on the exponential random variable, then we define this new stochastic process, which I denote simply by nt nu tilde, which is quite similar to the case of Takeda and Yano, but when we have this additional term in terms of this additive functional, which is this mixture of local time with respect to this limiting measure. And the function h is simply given in terms of the scale function of the Lévy process and this measure right here. So for any integral function, one can show that this stochastic process is actually a martingale. And then if at 0, this martingale is greater than 0, we have that the penalization limit converges as epsilon goes to infinity to this martingale change of measure. So now we have a really general class of penalization limits, and they are parameterized in terms of this limiting measure, which is nu tilde, right? And once again, we can take f simply as a indicator of 0 and obtain conditions of the Lévy process to avoid 0, which, as I mentioned, is quite interesting in order to characterize the Lévy, the excursion measure of the Lévy process away from a point. And just to fix ideas, because maybe it's simpler, let's consider the case that the additive function is absolutely continuous with respect to the Lévy measure. In this case, the conditions are simpler, meaning that in this case, the rate is all equal to Q and P when it's greater than gamma or 0. They convert to 0 as before, the same conditions for the Lévy process, but now we have that the rate goes to 0 point-wise, epsilon goes to 0, and we have this limit, which converges uniformly to this function omega, uniformly on compact sets in 0 gamma. So under these conditions, we have the same penalization limit, but now in this more simple case, then we have that the martingale looks like this in terms of this limiting function omega, and then we have the same penalization. So basically, it converges to this martingale change of measure under this martingale, right? And just to finish, just let me see how we can recover the penalization limits of Takeda. So basically, in the case that the omega function is simply given by epsilon, where we have an exponential clock, so the martingale looks like this. And we recover, of course, the results of Takeda and Yano for the exponential clock. We consider that the rate function is simply given by epsilon and the indicator of the positive half line, or it can be the negative half line. We obtain this martingale right here, and this corresponds to the penalization limit of the one heating time clock of Takeda and Yano. And basically, we consider this rate function, which is simply given by epsilon and gamma and 1 minus gamma in the positive or negative half line. We recover this penalization limit, and this corresponds to the 2 heating time clock of Takeda. But of course, we have a really general class of martingale measures limits of this penalization problem. And of course, for instance, one can take here the combinations of intervals or something like this to obtain new penalization limits, which can be interesting for conditions of the Lévy process to avoid points. And finally, I want to mention that, as in the Brownian case, one can also show that one can characterize the limiting change of measure simply as a concatenation now of a Brownian bridge and a Lévy process condition to avoid zero. And well, with this I finish, and thank you very much for your attention.
Thanks a lot, José Luis. Are there questions? I can make a question. So what is the relation between your scale function that speaks about heating times and the Feller story of scale function that speaks about heating probability?
Is basically the same, because actually by being the solution to the society problem, you can show that the scale function is harmonic, right? So basically, if you apply to the kill generator L minus Q, you have that is equal to 0. So basically it's the same, right? But for this particular case of working with Lévy processes, you have really nice characterization because it's given in terms of the Laplace transform, right? But for instance, it's basically the same object as in the case of diffusions. Right, so this is what allows you to obtain harmonic the generator. In this case, we will yield negative.
There another question or comment? Okay, so we meet next week. Yes. Bueno, pues entonces nos vemos la próxima semana.
They see us.
¿Cómo?
Can they see us? Yeah.
They can see us and probably Johnny too. I don't know if you're in the
Okay.
camera. That's the camera.
See you next week.
Bye.
Bye. See you next week.